Russia just fired off its massive Sarmat ICBM on May 12, 2026, from a silo up in northern Russia, and the whole thing worked perfectly.
Есть вот, приказ введен.
This rocket weighs 208 tons, stands 35 meters tall, and hauls up to 10 tons of warheads. Putin confirmed the test and pointed out the missile covers more than 35,000 kilometers along a suborbital path. That reach means it hits any spot on the planet with serious power. The engineering mixes rocket propulsion, orbital mechanics, and smart guidance systems, turning wild ideas into real flight. Picture the whole trip from silo to target and see exactly how this thing climbs into space and delivers its payload. The action starts inside a tough underground silo at Plesetsk Cosmodrome. Crews load the Sarmat with liquid propellants, a hot blend of unsymmetrical dimethylhydrazine fuel and nitrogen tetroxide oxidizer. These chemicals ignite on contact and create huge heat plus expanding gases. The first stage lights its powerful liquid rocket engines and generates thrust like hundreds of jetliners blasting off at once. Flames shoot out the nozzles hotter than 3,000 degrees Celsius and drive the whole vehicle straight up with acceleration several times stronger than normal gravity. In seconds, the missile clears the launch tower and climbs fast through the dense lower atmosphere. The boost phase runs about 2 minutes on the first stage. The rocket speeds up from standstill to several kilometers per second while onboard computers tweak the thrust by swiveling the engine nozzles. Think of it like steering a speedboat by angling the propeller. The Sarmat drops its empty first stage around 50 kilometers up where the air gets thinner. The second stage fires right away and keeps the push going higher and faster. A third stage follows, each one lighter than the last, so the vehicle builds speed efficiently. This stage setup follows the classic rocket equation from Konstantin Tsiolkovsky over a century ago. Every stage sheds dead weight and lets the rest turn every drop of fuel into extra velocity. It feels like a relay race where each runner carries less load and sprints harder toward the finish in space. When the final stage burns out, the Sarmat hits nearly 7 kilometers per second, roughly 25,000 kilometers per hour. By then, the missile sits above 100 kilometers, crossing the Kármán line that marks the start of space. Wings and air-breathing engines stay useless here because the atmosphere disappears completely. The vehicle coasts along on pure momentum, exactly like a stone thrown so hard it sails way over the horizon before gravity curves it back down. This coasting phase creates the suborbital trajectory that gives the Sarmat its huge range. Normal ballistic missiles trace a simple high arc rising maybe 1,000 to 2,000 kilometers and covering 10,000 to 16,000 kilometers horizontally. The Sarmat takes a smarter route. Its guidance computers set a flatter, faster path that rides right along the edge of low Earth orbit. The missile reaches speeds close to the 7.8 kilometers per second needed for a full circle around Earth. Instead of finishing the full orbit, the engineers shape the path so the vehicle travels a long slice of the planet's circumference before gravity plus a small deorbit burn curve it down toward the target. This fractional orbital approach lets the missile cover more than 35,000 kilometers, nearly the full circle around Earth, by picking routes over the poles or anywhere else. Imagine driving a giant circular highway around the world and exiting at the exact ramp you need. The suborbital path doubles the reach compared with a pure ballistic arc and sends the warheads in from angles that keep defensive radars guessing. While coasting through space, the missile bus releases multiple independently targetable reentry vehicles. Each warhead rides inside its own protective cone and gets its own small rocket motor for last-minute tweaks. The bus also carries hypersonic glide vehicles like the Avangard that detach and surf at Mach 20 or faster while maneuvering high up. These glide vehicles ride their own shockwave like a surfer, carving a wave and shift direction mid-flight to stay ahead of interceptors. All this happens in vacuum where temperatures plunge to minus 270 degrees Celsius and the sun's radiation hits hard with ultraviolet light. The onboard inertial navigation system plus star trackers that lock onto constellations update the course perfectly so every warhead lines up within meters of its target after crossing half the planet. Now the reentry phase brings the wildest part of the ride. As the warheads dive back into the atmosphere at 7 kilometers per second, they squeeze the air ahead into a glowing plasma sheath hotter than the sun's surface. Friction heats the nose cone to thousands of degrees and creates a brilliant fireball visible from orbit. Special ablative materials on the heat shield burn away layer by layer and carry the extreme heat off just like sweat evaporating to cool your skin on a hot day. Inside the shield, the nuclear payload stays cool and safe thanks to layers of carbon phenolic composites and insulating foam. The warhead slows from orbital speed to supersonic in under a minute while pulling forces up to 100 times normal gravity. The electronics and detonators survive because engineers run every part through giant centrifuges and plasma wind tunnels that copy the exact conditions. Guidance in re-entry uses inertial sensors plus terrain-matching radar or satellite updates. The warhead steers with small fins or thrusters like a falcon diving on prey. In the final kilometers, the fuse triggers at the perfect altitude and releases energy equal to hundreds of thousands of tons of TNT in a split second. The blast forms a fireball shockwave and electromagnetic pulse that knocks out electronics across a wide zone. The Sarmat carries up to 10 or more warheads, so one launch hits several cities or tough targets at the same time with pinpoint accuracy. The science powering everything comes down to physics anyone sees in everyday life. Newton's first law explains the coast through space. Once the engines quit, an object keeps moving straight until an outside force changes it. Gravity supplies that force and bends the path into a giant curve around Earth. Kepler's laws lay out the exact ellipses. These paths follow the same rules that hold satellites in orbit and guide comets past the sun. Rocket thrust comes from conservation of momentum. Hot gases blast backward at high speed and push the missile forward with equal force like a skateboarder shoving against the ground to roll ahead. Engineers run every number through supercomputers that model airflow heat transfer and tiny gravity changes from Earth's flattened shape. They fire engines on test stands that measure millions of pounds of thrust while cameras catch the flame patterns. They simulate full flights in virtual setups before lighting a real motor. The May 12 test covered its planned route to Kamchatka with every goal met right on time. The same tech scales up to the 35,000-kilometer global reach when crews pick the suborbital profile. This capability builds on decades of Russian rocket know-how that started with the R-7, the first ICBM, and the rocket that orbited Sputnik in 1957. The Sarmat upgrades the old R-36 Voevoda known as Satan by adding digital controls, lighter composites, and heavier payload capacity. Its 10-ton throw weight lets it carry decoys, chaff, and jammers along with real warheads and overload any missile defense. The suborbital option adds surprise by letting planners pick flight times and approach directions that keep everyone guessing. Every part shows smart trade-offs. Liquid engines deliver high efficiency and throttle control, though they need fueling right before launch. Solid boosters light faster yet give less flexibility for the long coast. The 208-ton mass needs a huge silo with shock absorbers to handle nearby blasts. The 35-meter length fits exactly inside hardened underground tubes. Redundant power supplies, radiation-hardened computers, and triple-check software keep everything running even in tough war conditions. Launch footage shows the raw power. This test marks a big step in strategic rocketry. The Sarmat enters service by the end of 2026 and replaces older systems while keeping the deterrence balance through unmatched reach and toughness. Its suborbital path shows mastery of space as part of the battlefield where physics itself becomes a tool for global strikes. From the chemistry of the propellants to the plasma physics of re-entry and the celestial mechanics of the trajectory, every element works together to send the missile through space and back to Earth with precision over distances spanning continents and oceans.